So today, like mentioned, I'll be talking about multifunctional anti-foaming Gemini surfactants, and we'll be exploring some new technologies that they had used to try to develop new materials building on this platform. So just a quick overview of the talk today. So we'll first go through a little bit about acetylenic diols, talk about the history, their performance and applications. Then we'll move into surfactants and their impact on the environment and some regulatory challenges that we're seeing in this area. We'll then explore some alternative chemistries and their performance properties. And then lastly, we'll understand those EH&S challenges and how they contribute to the development of new surfactants, and then we'll draw some conclusions. So to begin, the paint industry has seen, a wide variety of changes throughout the period. Most notably, probably, is the rise of latex paint technology and the introduction of water-based paint. So if we look on this, little timeline here, from the 1940s to, today, we've seen a great rise in latex paint technology and this water-based space. And with this introduced a lot of challenges, some of this being driven through the Clean Air Act of the 1970s. But with this switch to water-based, it introduced a large number of application and performance challenges. One, just surrounding around water as a solvent itself. This high surface tension of this material required or brought challenges and difficulties in wetting surfaces. Rheology control, there's, significant problems that arose there. And, additionally, there's a different drying profile. It's very sensitive to the environment and the temperature and humidity, and all of this required a new focus on the additives we use in our paint. So, like I mentioned, this, the story begins with the U.S. Clean Air Act. And, there was a large development of waterborne coatings. And when we just focus on that one piece of the high surface tension of water, that is, required surfactants to be able to wet many substrates. And the existing surfactants that were out in the market had been designed for cleaning and emulsifying. And these, molecules interacted together to form micelles. But this introduced the problem of stabilizing emulsions and foam. And it did lower the equilibrated surface tension, but it did not lower the surface tension under dynamic coatings. And the coating process is very dynamic, from the high speeds of the shear rates of application and needing to, rearrange itself to dry properly. And so this brought the need for new surfactants. And one of the solutions that was introduced are low foam dynamic wetting agents, and this helped enable the conversion to waterborne, right? So, many coating processes create large surfaces quickly, and post stirring or spraying, these materials need to rearrange. And so they must rapidly migrate to these new interfaces to achieve uniform wetting. And so, dynamic wetting is also needed with milling pigments and fillers because they must displace foam. And so looking for materials that provide this is essential. So when we talk about surfactants and defoamers, they create competition between wetting and defoaming. So, working with water-based paints, we have a wetting problem. So we have surface defects and the, appearance of craters and fisheyes. So what do? You add a surfactant. The surfactants that were typically on the market, the conventional surfactants, stabilize foam. So now you have a foam problem. So what do? You add a defoamer to defoam, to get rid of this foam. But now you have to add a defoamer, which can cause wetting problems and surface defects because they focus on working on that incompatibility to help eliminate the foam. And so we have this constant, circular process of we're adding things to solve a problem, but we're generating more problems. And this cycle can be, eliminated with the use of molecular defoamers. And this is where I guess we'll enter that in the next slide. But when we look at the, additives that were available for latex paints for the water-based market, and with the shift to, water-based automotive paints, the wetting agents we have available to us, the alkylphenol ethoxylates, traditional soaps, have poor spray performance properties and can be foamy. And the defoamers that we can use, mineral oils and silicone emulsions, can cause craters. So this really brought into light that we need something specifically for the automotive space that can help reduce these defects. And this is where the acetylenic diols enter the market. They are some of the earliest low foam dynamic wetting agents available. And this structure, shown down here, is a very specific structure, unique in its own way, that it is a lower molecular weight material, and these hydrophobes pack poorly, so they're not micellar. But they also have little interaction with other components in the coatings, and so this gives it the ability to function as a dynamic wetting agent, but also anti-foam or low foam. So when we look at the current, regulation that's been going on over the last few decades, the potential for surfactants to have adverse EH&S effects became apparent. So these materials were found in waterways in high levels. They persisted within the environment and can have slow or minimal biodegradation, as well as some aquatic toxicity. And so the regulatory agencies, including the US EPA, began to require more diligent assessments of these new chemicals. And particular attention was paid to impact on aquatic life. And building on this, we have been seeing some more regulations coming out within the European area about these surfactants. And, we're continuing to monitor and see what that looks like, but there's a lot of, potential impact on the surfactant market coming up. So the objective to develop, our next generation of acetylenic diol surfactants surrounds around achieving that excellent reduction of both equilibrated and dynamic surface tension while maintaining anti-foaming properties, but being less hazardous to the environment and their ability to be registered globally. And there's kind of two approaches that you could take to this. You could build on the current acetylenic diol platform, or you could explore new chemistries. And so in the next few slides, we'll start exploring these options that were covered. So first, building on the platform that exists today. So TMDD is the primary material, also following with the brand name Surfactants. And so this material, when we look at the equilibrated and dynamic surface tension data here, is excellent at lowering both of those properties. When we look at two other materials that are fall in this acetylenic diol classification, we see that the top one doesn't do a great job at lowering the surface tension compared to that of the TMDD baseline. And the chemical on the bottom row there, we do see similar performance in equilibrated, but we're not seeing a drastic reduction in the dynamic surface tension. And so, with this, it looks like they kind of found the sweet spot with TMDD, and numerous other, acetylenic glycols were synthesized, but few showed promise, and most were not registered on TSCA or REACH. So when we move into the next kind of phase of exploration, we looked into alkoxylation of these acetylenic diols. And so the first one is TMDD in this series. And when we look at the varying degrees of ethoxylation, we can see that the HLB increases, the water solubility increases of these materials, the foam control properties decrease, and there was some ability to stabilize oil and water emulsions. And when we look at all of these materials, we do see varying performance in regards to the equilibrated and dynamic surface tension. But in general, as the alkoxylation increases, the influence of the acetylenic diol on performance decreased, just due to general size of materials. So the lower molecular weight alkoxylates, showed better performance, but they would require product registration due to their size. And when we look at these branched alcohol alkoxylates in a dilute emulsion system, moving a bit more towards what a paint formulation may appear. So on the, this table here, we see excellent performance with these materials in regards to equilibrated and dynamic surface tension properties of the aqueous surfactant solutions. But as soon as we begin to put them into dilute emulsion, when we track the surface tension here over bubble frequency, we see that they do not compare to that of the TMDD baseline control. And this suggests that there is a greater interaction between the latexes and the other materials in the formulation that reduce their overall performance. And when we look at this same series and we look at their ability to control foam, so those same samples, so TMDD, the baseline control, shows excellent foam control or no foam generation. And when we look at the alcohol ethoxylates, they have varying foam performance, showing that these materials, while they may perform in aqueous surfactant solutions similar to TMDD, they are not performing in a more formulated coatings space, showing some limitations of these new materials. And with that, many other alternative low foam surfactants were evaluated, and some of the learnings from this. So several structural features were found. So short, often branched hydrophobes prevented that strong micelle formulation and interaction with system components. And materials with relatively low molecular weights saw better performance. But these lower molecular weights cannot always meet the USA EPA definition of low-risk polymers, requiring significant time and testing costs for registration in the U.S., as well as, for global registration, significant problems or significant costs would come into play as well. So from there, they continued to focus on just the space that we saw great use with these acetylenic diols. So a next generation surfactant project was focused on developing new materials for automotive OEM coatings and other applications. And in this set of data we're going to look at base coat and primer formulations, all while keeping in mind, right, excellent reduction of equilibrated and dynamic surface tension, low foam, but the ability to be registered and less hazardous. And so we'll talk through 3 or 4 different classes of chemistries that were explored. So the first is building on the alkoxylated acetylene diols, and we'll explore 2 samples, which will be A1 and A2. When we move into the next class, the dialkyl ureas and amides. So these are non-acetylenic chemistries with S104-like performance. And so these materials were equal or better at defoaming than S104, but they were toxic and difficult to solubilize. And the last class we'll explore are these dialkyl malates and tartrates, which were biodegradable, low odor, but they do have poor chemical stability, typically they will undergo hydrolysis at basic conditions, so pH greater than 7.5. So here are the two model formulations that we tested. So the first is a metallic base coat, and the second is a primer filler. So in this work, we saw a reduction in surface defects, most notably when we look at this AE surfactant, which I believe is the D3 surfactant in this series. We see excellent reduction in surface defects, and that these additives can help eliminate the differences with surface tension, and the alcohol alkoxylates showed some slightly improved performance compared to the silicone surfactants that one could use for surface tension reduction. And when we look at the flow and leveling properties of these materials, which can be caused by surface tension differences arising from solvent evaporation or differences, this data set shows a comparison of long wave and short wave orange peel evaluation. So all the way on the left-hand side, we have our standard here. We have the incumbent, TMDD type-based products. And then we have D3, which is the sample here. I apologize. I think my phone's vibrating. And so here, when we look at the comparison against some secondary alcohol alkoxylates and some silicone-based surfactants, we see excellent reduction in both the short wave and long wave properties with this D3 material. And when we look at these samples as a whole, all of the different chemistries that were evaluated, I know there's a lot going on in this plot, but most notably to note is the dark purple line kind of shown here is the incumbent TMDD. And so all of these samples that were tested showed varying differences in the overall performance of, we're trying to meet TMDD, but we see a large variety of different performance showing that, there's a lot of factors going in and maybe not one is an exact match for this. And, that's the way, sometimes it goes that we don't, we're unable with the technologies we have to meet those challenges. So just a quick, overall summary of that experimental surfactant screening that was completed. So in the base coat, the TMDD continued to be the most effective in that dynamic surface tension reduction. And it did have the greatest impact on the base coat rheology. And the experimental products B2 and A2 gave the closest performance to TMDD. And when we move into the primer surfacer series, the experimental surfactants gave improved foam control, but TMDD continued to be the best for surface tension reduction. And so, from this work, overall, it was, found that a new approach needs to be taken, that there was no clear solution found in this screening work. And so that's when we move into focusing on early EH&S testing and adding this into the new development process. So many low foam dynamic wetting agents have the potential to be aquatically toxic and slow to biodegrade. And so with this, efforts were directed at building structure property relationships that include the EH&S properties. And at this point, there was 10 years of existing chemical structure property relationships that provided learning. So branched alkyl groups of the same number of carbons produce low foam wetting agents. More hydrophobic molecules are lower in foam, and smaller molecules can help reduce the surface tension. And so with all of this information, as well as building upon the EH&S standards, we moved into 3 new classes of surfactants that were identified. And so we'll show in the next few slides some of the data surrounding these materials, focusing on the biodegradability, as well as the impact on aquatic life. And so 3 classes of materials were identified: the N,N-dialkylglucamines, thioethers, and hydroxythioethers. Most notably, we will talk about the U-136 in this series. And we focus on just optimizing the aquatic toxicity and biodegradability within this series. And when we increase the branching and carbon in the hydrophobe chain, we see varying performance of both the marine algae toxicity, shown on this side of the y-axis with the blue bars, and on the right-hand side, the percent of marine biodegradation after 20 days, and higher parameters for both of these, higher values for both of these parameters is ideal. And so you can see here, what works for one might not work for the other parameter we're evaluating. But we did identify the closest prototype compared to that of TMDD. So shown here would be in the purple curve is this U-136 wetting superwetter agent. And we do see excellent reduction in the dynamic surface tension compared to the control, which is that top blue curve. Just a quick summary of these prototypes most likely to achieve global registration, because that was an important part of this series, is understanding whether they also have an EH&S profile. So the U-136 showed promise in both the coatings and graphic arts market as an organic superwetter. So it's great for wetting hydrophobic substrates, coalescing benefits with low foam, but it did see limited success in the OEM market. The thioether T115 performed as a molecular defoamer, and so we do see that used in some coatings formulations. And the N,N-dialkylglucamines were not taken forward in the coatings application industry, since it was less efficient at wetting and less effective at defoaming. So to summarize all of these data we shared with you, so TMDD has been the benchmark as a low foam surfactant in the automotive industry since the 1980s. The performance of TMDD is unique due to its low molecular weight and the branched Gemini structure. And global product registration can be a challenge. So the quest still continues for offsetting and replacing this TMDD material. So new prototypes are in early stage development, both for performance and EH&S profile at Evonik, but at this point we're not ready to share any of that. So with that, I first want to make sure I thank Jim Reeder for all of his help in preparing these slides. I know he can't be here today, as his last day will be tomorrow. He'll retire, but I want to make sure I thank him for all of his support and guidance on this work. And then lastly, I would like to thank all of you for your time and for attending my talk, and I'd be happy to answer any questions.
So Sarah, for questions, one of them is, for the regulatory activity, are you mainly tracking Europe, or are you still, paying a lot of attention to the U.S. agencies? They seem to be a little stalled in the media.
Yeah, so I think a lot of the regulations are coming out of Europe right now, and so we're focusing on that. I think there are trends that what happens in Europe makes its way to the U.S. eventually. So we're monitoring it both within the European region as well as where it's moving in the U.S.
And are you seeing anything on the horizon that is going to impact even the end users, the OEMs?
We haven't heard anything from the U.S. side. I think there might be some concerns with the hazards that may be carried going forward in the European region. So for those global brands, we might see an impact there.
Okay, thanks. Yeah, it's funny because it seems like more and more countries are coming up with their own versions of REACH and things like that, and it's really becoming a challenge to global companies. Yeah.
Absolutely.
Other questions?
Thank you very much. You showed in one graph about the biodegradability, and when this number of carbon was increasing, the biodegradability was increasing. Why do you think that's happening? Is that breaking to just lower, kind of smaller molecule, and that's how you're measuring biodegradability, or?
Let me go back and.
Yep.
That is a great question. I personally don't know much about this biodegradability testing myself, so I can follow up on that and get back to you. Because I guess based in my mind, I would think maybe it would be different as well.
So if you post that question on the Whova app, she'll receive that note and see who it is. She can respond directly to you. That work? Yeah? All right, very good. All right. Oh.
Thanks. Thanks for your talk. It was very interesting on this. With some of these newer, thioethers and all of this, and we talk about biodegradability, are we looking at how that then shows up in the coatings themselves, or is there any durability concerns of any color or any issues like that?
I don't believe they saw issues from that approach. This work happened a little bit before my time with the company, so I don't believe they saw issues. I think it was more they weren't performing quite the same from a surface tension perspective, so they weren't meeting. These weren't used as much in the OEM space due to this, issues reducing surface tension.
Thank you. Any other?